In this video, we're going to continue our study of electricity. Here we're going to introduce the concept of an electric field, and we'll also talk about the force on a charge in an electric field. In first semester physics, we introduced the concept of a gravitational field, but we don't use that concept very much. Here, in this course, we're going to be using the concept of an electric field and a magnetic field extensively. So let's first of all understand where this concept comes from. I say here on the slide that most forces in our everyday lives are contact forces. And what I mean by that is literally if you want to exert a force on something, you've got to make contact with it. So if you want to exert a force on the wall, you have to physically touch the wall and push on it. However, we know that there are forces that don't seem to act that way. Specifically, gravitational forces, electric and magnetic forces, can act over a distance. So in other words, the Earth doesn't have to be touching your pencil to exert a force on it. If you hold your pencil up above the Earth and let go, the Earth exerts a force and pulls the pencil down. Same thing we see with charged objects and also with magnetic objects, that they can exert a force over a distance. We refer to this as action at a distance. Now, one of the things that we realize pretty quickly when we have forces that can act over a distance is it brings up some really interesting questions. So for example, how quickly would the Earth react if something happened to the Sun? So in other words, here's the Sun, and here's the Earth orbiting the Sun. Well, how quickly would the Earth stop orbiting and just go off in a straight line if all of a sudden the Sun disappeared? You'll notice that there is no time in the universal law of gravitation. So it doesn't seem that we can answer that question by using that law. We have the exact same kind of question when it comes to the electrical force. If I've got a charge Q1 and I've got another charge over here Q2 separated by some distance r, when something happens to Q1, for example, maybe it moves, how quickly does Q2 know that something happened to Q1? Once again, there's no t in here. So the question is, are these forces instantaneous, or is there some time delay between when something happens to one of the objects and the other object responds? Well, let's look at the way that physicists currently view these forces. The way we view it is a little different than what we've talked about so far. So for example, instead of talking about the Earth exerting a force directly on the moon, what we now do instead is we say that the Earth creates a gravitational field. That field surrounds the object, and in fact a gravitational field surrounds every object that has mass. And the reason that the moon then experiences a force is not because the Earth directly exerts a force on the moon, it's because the moon is in the gravitational field created by the Earth. Now, why does that help to resolve this issue of action at a distance and time delay? Well, we now have a way to understand why there would be a time delay. In other words, picture the following. Let's say I've got a lake here, and in my lake I have a cork. So my cork is floating in the lake, and somewhere away from the cork I drop a rock into the water. Well, does the cork start instantly moving up and down? Well, you know the answer to that is no. That what has to happen is once the rock hits the water, that wave has to propagate, and once the wave propagates to where the cork is, now the cork will show that something happened farther away in the lake. That's exactly the way we envision what happens with gravity. In other words, if something happened to the Earth to shift it out of its orbit in some way, that change would have to propagate through the gravitational field created by the Earth. And when that propagation gets to the moon, that's when the moon would react. We envision the exact same thing for electricity. Now, up to this point, we've talked about the interaction between charges using Coulomb's law. We've said that charge Q1 directly exerts a force on charge 2. But the way we're now going to talk about this is that charge 1 creates an electric field. Charge 2 experiences a force not directly from Q1, but from the electric field created by Q1. And therefore, if we change, for example, the position of Q1, that change has to propagate through the electric field in order for Q2 to know that something has changed. So that's the modern way that we view this problem. By the way, both gravitational fields and electric fields propagate at the speed of light. So this concept of a field is one that you probably haven't seen before, or if you've had physics in high school, you probably didn't spend a lot of time really trying to understand. So I want to talk a little bit more about it with you. When we use the term field in physics, what we mean is a quantity that has a value for each point in space and time. So, for example, in the room where you are right now, there's a temperature field. You can imagine that, let's say in the corner of your room, you set up the origin for a coordinate system, and then for every point in your room, you could measure what the temperature is at that point in space. We know that the temperature would be higher towards the ceiling, it would be lower towards the floor, and also, of course, the temperature might change over time. So that's what we mean by a field. It's simply a quantity that has a value for each point in space and time. Now, the electric field is just one step more complicated than a temperature field because the electric field is an example of a vector field. And so that means in addition to just having a value or magnitude at any point in space, there's also a direction associated with each point in space. So let's see how we define the electric field. The electric field at a point P is defined as the force exerted on a tiny positive charge at that point divided by the magnitude of the test charge. So let's say I want to figure out, is there an electric field at this point right here in space? What would I do? Well, I would take a positive test charge. And by the way, the reason that we specify tiny is we don't want to affect the other charges that are actually creating the field at that point. Notice that it's a positive test charge. That's important. So we would take a little positive test charge and we would see what happens to it. Well, if it experiences a force when placed at that point in space, then we know there is an electric field at that point in space, and we define the electric field as that vector force on the charge divided by the magnitude of the charge. You'll notice that from this definition of the electric field, we can see that our units of electric field are newtons per coulomb. I'll just mention that later in the course, we're going to see that another unit for electric field is volts per meter. But for right now, we'll be using newtons per coulomb. Let's see if we can figure out the magnitude of the electric field created by a point charge. Now, in order to do this, so in other words, what is the electric field being created by this charge? In order to do this, we need two things. We need our definition of the electric field, which we just made, and we need Coulomb's law. So if I'm trying to figure out what is the electric field created by this charge, I know that what I want to do is I want to take a tiny test charge. It's got to be positive, and I'm going to call that Q2. So that's my test charge. And then what I need to do is figure out what is the force acting on that test charge, and then divide by the value of the test charge. Now we're here just going to do the magnitude of the field, so I'm going to not have vector signs here. So E is equal to the magnitude of the force on charge 2 divided by the magnitude of charge 2. Well, we know what the force is because we can use Coulomb's law. In other words, it's K Q1 Q2 over r squared, and then I want to divide that by Q2. You'll notice that what we get is that the electric field created by charge Q1 is just kQ1 over r squared. So the closer we are to a charge, the larger the electric field is created by that charge. So just dropping the number from the charge, here is our expression for the electric field created by a point charge. You'll notice in these diagrams, it's trying to illustrate the fact that the electric field decreases with distance from the charge. So you'll notice if we're close to this charge, the electric field is big. If we're farther away from the charge, the electric field is smaller, because we can see it goes down as 1 over r squared. Also notice that because by definition we defined the direction of the electric field to be the direction of the force on a positive test charge, well, that means that the electric field points away from positive charges, because if I put a positive test charge right here, it would be repelled. You'll also notice that that means that the electric field created by a negative charge goes towards the charge, because if I put a little positive test charge here, it would be attracted to the negative charge. So field goes away from positive charge, and the field goes towards a negative charge. By the way, one of the ways that we'll use to visualize electric fields just a little bit later in the course is we'll use the concept of field lines. And field lines just represent how strong the electric field is. They would point away from a positive charge and towards a negative charge. What if we know there's an electric field in a region of space and we now put a charge in that electric field? What happens? Well, we can take our definition of the electric field, that the electric field is F over Q, and we can rearrange that to find the force on a charge placed in an electric field. So for example, let's say that there is a constant electric field to the right. And I would denote that by just drawing evenly spaced parallel lines going to the right. So that's our electric field. If the electric field is in that direction, if I now put a charge Q, and let's say it's a positive charge, well, now if I know the magnitude of that electric field, I could figure out the force on that charge. I know that the direction is going to be in the direction of the electric field for a positive charge. And I would just use this formula to calculate the magnitude. Notice, by the way, that if in the same field instead I put a negative charge will always experience a force opposite the direction of the electric field. That's important because you'll notice that F and E are always in the same direction except if Q is negative, and then they're in opposite directions. So a positive charge put in an electric field will experience a force in the direction of the field. A negative charge put in an electric field will experience a force opposite the direction of the field. Let's talk about the superposition principle. We talked about the superposition principle for forces in our last video. It turns out that since the electric field is so closely related to force, if the superposition principle works for forces, it works for electric fields as well. So let's see what exactly it is we're talking about. Here it says if the electric field is due to more than one charge, the individual fields due to each charge are added vectorially to get the field at any point. So let me do a quick example just so you can see what we're talking about here. Let's say that I have a positive charge, Q1, and down here, let's say I have a negative charge, Q2, and let's say right here I've got another negative charge, Q3. And I want to know what is the electric field right here at this point in space. So the question is, what is E right there. Well, I know various things. I know that the electric field created by a positive charge goes away from the charge. So the electric field created at this point in space due to Q1 would be in that direction. So I'll call that E1. The electric field created by charge Q3, since Q3 is negative, it would be towards it. I'm going to draw it a little bit bigger because Q3 is closer to that point. And the electric field created by charge 2 at that point would also be towards it. I'll make that one a little bit smaller because Q2 is farthest away. So those would be the three electric fields created by those three charges at this point in space. Okay? So there's nothing at that point in space except the electric field itself. So how would we find the net electric field, or the total electric field at that point in space? Well, it's just vector addition again. I would take E1, I would add E3, then add E2, and my resultant electric field at that point in space would simply be that vector. Okay, so that's what we mean when we say that electric fields behave the superposition principle. They simply add vectorially, just as you would think they would. So let's do a problem to illustrate this. The question is, what's the magnitude and the direction of the electric field at the red dot? So there's nothing here. It's just a point in space. We want to figure out the electric field created by those two charges at that point. So the first thing we want to notice is that since Q1 is positive, the electric field created by Q1 would be in that direction. Q2 is negative, so the electric field created by Q2 at that point would be in that direction. Also, notice that Q2 is both a bigger charge and is closer than Q1. And therefore, I know that the electric field created by charge 2 is going to be bigger in magnitude than the electric field created by charge 1. So I can get a rough idea of what I'm looking for here if I just add E1 and E2. The actual net electric field at that point in space should be a vector that looks something like that. And so let's go through and figure out the details of finding that vector. You'll notice this is very similar to the Coulomb's law type of problems we did earlier, but here it's important to understand we're not looking for force, we're looking for field. So the first step in this process is just to find what are the magnitudes of those two electric fields. So in other words, we know that E1 looks like that, we know that E2 looks like that. Let's figure out those magnitudes. Well, we're just going to use the fact that the electric field is kq over r squared for a point charge. So for the electric field created by charge 1 at that red dot, it would be 9 times 10 to the 9th, our value of k, times our charge, which is 15 times 10 to the negative 6th coulombs, divided by the distance to that point in space, which is 0.60, and I've got to square it. If you calculate that, you should get 3.75 times 10 to the 5th newtons per coulomb. Let's calculate the electric field at the red dot created by charge 2. That's going to be 9 times 10 to the 9th times the value of charge 2. Remember here, we're finding the magnitude of the field, so I want the absolute value of the charge. That's 30 times 10 to the negative 6th. And I'm dividing by the distance, which is 0.3, and I got to square that. If you calculate that, you should get 3 times 10 to the 6th newtons per coulomb. Notice that E2 is almost 10 times bigger than E1. In fact, it's 8 times bigger if you look at the numbers. And we can see why that is. It's because we're closer to a bigger charge. All right, so that's our first step. The next step, just like in any other vector addition problem, is we know we need to find the components. So remember that E1 is that vector. So let's just kind of enlarge that a little bit. Here's E1. You'll notice that it makes an angle relative to the x-axis of 30 degrees. And so the x component, E1x, is just E1 cosine theta. And obviously here we want to be in degree mode. So if you plug in the value we got before, 3.75 times 10 to the fifth, and the cosine of 30 degrees, you should get 3.25 times 10 to the fifth newtons per coulomb. So that's our x component. Our y component would be E1 sine theta. And I'll just let you know what I got when I did it. I got 1.88 times 10 to the fifth newtons per coulomb. So those are the components of E1. Now E2 is easier. E2 is straight down. And so we don't really have to do any math, but we do have to be a little bit careful. If we've got a vector that looks like that, we know that the x component of that vector is going to be 0. That's the obvious part. The y component, though, notice it's pointing down, not up. So it's going to be negative the magnitude that we got previously. Okay, so now we've got the components of the two electric fields that we're trying to add. We know that the next step in vector addition is to add those components and to find the components of the resultant electric field. In other words, the x component of the total field at that red dot is just going to be the sum of the components, the x components of the electric fields. And in the same way, the y component of the resultant electric field is just going to be the sum of E1y and E2y. So what you get here is 3.25 times 10 to the fifth newtons per coulomb. And here, and of course there we didn't have to do any addition because E2x was 0. For the other one, we have 1.88 times 10 to the fifth, and then we're adding negative 3 times 10 to the sixth. And so what we get there is negative 2.82 times 10 to the sixth newtons per coulomb. Our final step then to find the electric field at that point is to find the magnitude and the direction. And we've done this many times now, so I'm just going to remind you. Of course, it's using the Pythagorean theorem to find the magnitude of the electric field. And when I calculated that, I got 2.83 times 10 to the sixth newtons per coulomb. And again, you should always go and calculate these yourself and make sure that you get the same answers. In terms of what the vector looks like, we know that we have a negative y component and not very much of an x component. And so this angle theta is just going to be the inverse tangent of EY over EX. And I got negative 83 degrees. Okay, so that's the electric field at that point in space. So what would happen if we now place a charge at that red dot, at that point in space where we know the electric field? So if Q3 equals negative 25 microcoulombs is placed at the red dot, what is the magnitude and the direction of the force on it? Now, one of the ways you could do that is just use Coulomb's law as we've done before. But that would be a waste of effort because we already know what the electric field is at that point. If we know the electric field at a point in space, then we can calculate the force on a charge that we now place in that electric field. The magnitude of the force is just going to be Q times E. So in other words, we take our 25 microcoulomb charge, multiply it by the magnitude of the electric field that we got up above, and what we get is a force of 71 newtons. Now, what would the angle be? Here we've got to be a little bit careful. We know at that red dot there is an electric field that is making an angle of negative 83 degrees relative to the x-axis. However, the correct answer for the direction of the force on a negative charge, if we placed it there, would be the opposite direction, because we know that the force on a negative charge is always opposite the direction of the electric field. And so we'd want to add 180 degrees to that negative 83, and so our direction for the force on that charge would be 97 degrees. Okay, so you may have noticed that this problem was very similar to a problem that we did in a previous video. And that's because I wanted to illustrate our new way of thinking versus our old way. The first time we did this problem, we did it using Coulomb's law. And remember, we were trying to find what's the force on this charge due to each of these two charges. And we found the force directly with Coulomb's law. But I've told you that the more modern way to think about this is that charges create electric fields. And then if you put a charge in an electric field, it will experience a force. So the way we just did it is we first found what is the electric field created by these two charges at this point. Once we knew the electric field at that point, we then placed a charge there and asked what the force was. And of course we got the same answer because it's got to work out the same both ways. So remember that the way we envision things now is charges create electric fields, and then if I put a charge in that electric field, it will experience a force. So finally, just to summarize the two really important things we've talked about today. Charges create electric fields. If you have a charge, it's always creating an electric field. Just like if you have a mass, it's always creating a gravitational field. Also, if you take a charge and you place it in an electric field, it will experience a force. So charges create electric fields. If you take a charge and place it in an electric field created by other charges, it will experience a force.